Hey, welcome back to Math with Patrick. Today is April 21st, and we're solving problem number 111 from this Daily Epsilon calendar. I would have held it up today, but Quill is currently lying on it. All right, so the answer is 21, and we need to make sense of all of this notation and show that x is 21 today. So I see that we have a sequence where I'll put this in a table where I have some kind of number here, which tells me like what term of the sequence I have. And then this other value where I have f and then the subscript of the number is kind of tracking the value. So when my value n is 1, I'll say f sub n is also, or sorry, f sub 1 is also 1. And then so my second term in my sequence lines up when n is 2, and f sub 2 is also 1. And then now we have this rule that kicks off the rest of the terms in this sequence f. And maybe you recognize it. This is the Fibonacci sequence, where to figure out what f sub 3 is, we're going to do f sub 2, see how that's 3 minus 1, plus f sub 1, because this is 3 minus 2, or 1. So to find f sub 3, that's when n is 3. This just tells me add the two previous values. So 1 plus 1 is 2. And then now when I increment this to 4, and I want to find what f sub 4 is, then same thing. This number is just 3. This number is just 2. And then this instruction is telling me to add f sub 3 and f sub 2, or essentially the previous two numbers. And this pattern is just going to roll all the way up to basically as far as you can count. I'll go for, well, let's see, how many terms should I get? Maybe like 8 or 9, because I can see like an f sub 9 over here. So I'll go 5, 6, 7, 8, 9, and hopefully this is where I can stop. Let's see, 1 plus 2 is 3, 2 and 3 make a 5, that's an 8, a 13, a 21, and then a 34. Okay, hopefully that's all I need for today's problem. And of course, the sequence keeps on going, right? The next term is going to be 55, but we don't have to go that far, hopefully. Now let's make sense of what's going on here. Anytime you see this big sigma character, this is for a sum. And basically, let's just walk through step by step what this sum is doing, and maybe we can make sense of it together. Essentially, what you do is you plug in this 1 into wherever you see the value I. So it looks like I'm going to plug in a 1 here. And then I'm going to do whatever math I need to do here. And then once I find that value, I'm going to add it to the next one when I is equal to 2. And then I'm going to plug in a 2 right here, do whatever math I need to do. And then I'm going to add the next thing when I is equal to 3. And then I'm going to keep doing that pattern up until I is equal to 8. That's this top number right here. And hopefully by the time I've done all of that, x is going to be 21 today. So when I is 1, I get f sub 1 squared over f sub 9. And I think I'll just write it out this way for a little bit. F sub 2 squared over f sub 9, because this one isn't changing at all, right? And it's just when I'm incrementing this value of I, that's really the only thing that's changing. And so I'm going to have all of these terms. I'll write the next one, f sub 3 squared over f sub 9. And then it's going to go all the way up to f sub 8 squared over f sub 9. Okay. So it looks like I have a whole bunch of fractions all being added up. The denominator stays the same the whole time. And so like even like trying to do another example with more concrete numbers, like if I had like a third plus 2/3 plus 10/3, whenever you're doing fraction math and adding them up, if you have a common denominator, you just kind of keep the denominator the same and then add up all of your numerators. So that's what I'm going to plan to do here. I think it would be best to do this dividing by 34 at the very end. and then worry about adding up the numerators first, then dividing by 34. So that's what I'm going to do here. It's going to be a long numerator, but then 34 on the bottom. And then I'm just going to square up all of these numbers. Let me zoom out a touch. And it's going to be the squares of all the numbers 1 through 8. So it'll be 1 squared plus 1 squared plus 2 squared plus 3 squared. And I'm just reading off that table up there up until I reach that 21. Okay. So apparently this fraction that I just wrote with all of these square numbers, then finally divided by 34, is going to be 21, today's date. And I don't really see a good way to do this like efficiently. Squaring these numbers won't take too long, so I'll just solve it directly. I'm going to get 1, 1, 4, 9, 25, 64. 13 squared is 169, and then 21 squared is 441. Then I'm going to divide all of these by 34. Okay, I mean, basically it's just some arithmetic until I show that this number is 21. So 1 and 1 makes 2, 6, 15, 40, 104, and then I can't do the rest in my head. So I'll add all of these up. And yeah, this 104 is coming from adding up as many of the terms as I could quickly in my head. 1 and 9 make a 10, plus a 4 makes a 14. This makes an 11, and then 4, 1, 1, 1 makes 714. And then hopefully once I do the long division here, I'm going to get the number 21. Looks like 34 goes into 71 twice, because that makes a 68. And then doing the little subtraction step, looks like I need to borrow, or maybe you can just kind of tell that these two numbers are 3 apart. And so once we get the 3 and drop down the 4, 34 goes into 34 just once. So here is the 21. That's the answer for today, and we're all done. So you should stick around for a little bit. I thought it was kind of weird that there was a 21 that already showed up in our problem today. And what I mean by already showed up is that when we look into this table of the Fibonacci numbers, this 21 right here, this was just generated by the Fibonacci sequence, and we found that 21 kind of first in a way. And after doing all of that complicated math, it came back around again. And oftentimes these Daily Epsilon problems have these interesting patterns hiding like underneath the surface, behind the curtain. And so I just wanted to see if today is one of them. So let's see, what is that value? We were doing the sum from, okay, I'll change this to I to match the calendar. I equals 1 to 8. There it is. And then we did, I know that there are subscripts in the calendar, but I think Desmos is going to understand it better if I use function notation instead. So we're going to square the top and then just have f of 9 on the bottom. So there's the 21 that I calculated earlier. But I wanted to check and see if I can generalize this process. And my guess is that this is just secretly the Fibonacci sequence, just more complicated. So instead of an 8 here, what if I do an n? And you know how this was like a 9? So I'm guessing I could put an n plus 1 to be like 1 more than 8. And then if I attach a slider here, let me make n go from, well, it wouldn't make sense to be 0, because then like going from I equals 1 to 0, like usually the top number is bigger. And it might not even make sense for n to be 1. Let me see, does that make any sense? Because then I would plug in f of 1 here and f of 2. I think that'd be fine. So let's see, n will range from 1 to 10. And this step just makes sure that I'll step up by whole numbers, because if you don't include that step, then you're going to have all of these decimals, and my sum isn't really defined for any of those decimal numbers. Okay, and my hunch is that these numbers are just the Fibonacci numbers like already. So here again, this was me putting that 8 up top, and so that puts the 9 back here on bottom, and there's this 21 again that we already solved for. But if I go to the previous one, yeah, that's just 13. Then that's just 8, And now I'm looking here on the table, and so it should be 5, 3, 2, 1, 1 when I tick these down a little bit. 5, 3, 2, 1, 1. Yeah, okay. And then the next one is 34. And then I said in the video that 55 is the next number. And so there it is. So this sum is just the Fibonacci sequence, but expressed in like a different complicated way. Or at least I'm pretty sure it is. So this equation right here is exactly what we were doing on the Desmos screen, where I was taking the sum of the first n Fibonacci numbers, and I squared them, then summed them up, then finally divided by the next one. And all of the ones that we checked ended up being equal to the nth Fibonacci number. But maybe this pattern breaks when n is 11 or 20 or a million. And so just to be sure, I'm going to use induction to prove what we both think is true from looking at the Desmos thing. Using mathematical induction, you need to prove two things. You need to prove a base case, which just means you need to show that this is true somewhere. And we already did that. We already saw that this is true for the first like 9 sums in this table. So I'm not going to do that on the paper or on the whiteboard here. All I need to do is show the inductive step. That's where I'm going to assume that some step is true. And from that assumption, I should be able to prove that the next one is true. And then so that way, like if I know that when n is 9, this equation works, then proving that inductive step will tell me that when n is 10, it'll also still work. But then I can then apply that on the 10th step, and that'll show me that the 11th step will work. And then we can just kind of keep stepping up until infinity. So basically, I will assume that some step in this, maybe when n is this random number k out there, that this is actually going to definitely work out. And I know that it will work out for small values of k, right? Because we already saw that on Desmos. And so it's safe to assume that it's going to work somewhere. And let's see, I think I'll just copy exactly what I see, but instead of an n, I'm going to put a k here just to represent some number out there. Maybe k is 100 or 1,000 or something. And I'm assuming that this is true, that this is actually indeed equal to f sub k. And I want to show, or I want to prove, that this equality will hold for the next one. And so anytime I see a k, I'm going to put a k plus 1, because that's going to be the next number after k. So I want to show that when I sum up all the terms to k plus 1, and the terms should look basically the same, although I guess here I'll have a f sub k plus 2, because again, I'm incrementing k up by 1, and so the next number after k plus 1 is going to be k plus 2. And this should all be equal to f sub k plus 1. I need to use some of this information to help me out here. And I think what might be useful is to actually rewrite what's going on with this one. You know how earlier I was able to like add up all my terms, then divide by this denominator? So from my assumption in this step, I know that I could just rewrite the sum of all these squares. So just like the f sub I squared, I know that's going to be equal to f sub k times f sub k plus 1. That's essentially just me multiplying this denominator over here using like an algebra step. And so I'm pretty confident, very confident even, that this is also true based on my assumption here. And I'm hoping that I'll be able to find this guy, this sum of all the square Fibonacci numbers, somewhere in here. So let's see. I want to break up this sum on the left. I'm going to do the sum from I equals 1 to k of the exact same thing. So it's just going to be f sub I squared over f sub k plus 2. And then the last term would be me plugging in this k plus 1 for that I right there. So the last term will be f sub k plus 1. We're going to square that, and then finally divide that by f sub k plus 2. And I'm still not quite sure or convinced that this is going to be equal to f sub k plus 1, but that's what I hope to prove. And let's see. So this part right here, this is the sum of the squared Fibonacci terms, each of them divided by this f sub k plus 2 number. But I also know that kind of like what I was saying before, that denominator, I could either do it at the very end or for each term. It didn't really matter where I put it. I know that I could factor that out kind of like this. This is me kind of like doing that divide by 34 at the very end, and that totally worked out for the problem earlier. And, this term is still going to be right here. And so now I have the sum of the squared Fibonacci terms up until some number. And based on my assumption, I know that I can rewrite it as just a product of f sub k times f sub k plus 1. So I want to replace this part with f sub k times f sub k plus 1. I guess I'll just keep this f sub k plus 2 down here. And then let's just keep the same thing going over here. So it looks like I have the same denominator, so might as well just share it. See how the denominator is still f sub k plus 2. And still, I somehow need to show or argue why this fraction is just the same as that. What could I do? I want to center this number just so it looks, a bit more in the middle. And okay, I have a shared factor here, right? I have a f sub k plus 1 in this term and that term. So if I factor it out, f sub k plus 1, I'll have f sub k and then plus f sub k plus 1 here. So you could redistribute this term, and then you're going to get back to this sum on top. And then finally, I'm going to just put this denominator back here where it's supposed to go. And then I'm going to use the same rule that we used to generate all the Fibonacci numbers. I know that f sub k plus f sub k plus 1, these are the two terms preceding f sub k plus 2. And so this number right here is just the same as that, f sub k plus 2. There we go. So now I can cancel off common factors in my fraction. And so ultimately, I'm just left with this number. And so this is equal to that, which is equal to this. And basically, I have shown that these two values, the one on the left side of the equation and the one on the right, indeed have just been the same number all along. So using induction, I am now very confident that this is an equality that always holds. And so it wasn't really special that, there's an 8 or a 9 here. Well, I guess, it was very important to get this 21 in the list. But, if today's date was the 13th, we could have just written a 7 here and an 8 here, and this problem would have just stood just the same way. Or, if today's date was the 8th, we could lower these down by another 1 each. Cool. So I just wanted to make sure that the hunch that I had with the slider was actually a true mathematical fact. And I didn't know this about the Fibonacci numbers, that you can do this weird squaring and summing and dividing, and then you can get back to one of the numbers in the list. So I learned something today. I hope you did too. And I'll see you in the next video. Bye.